Good morning, everyone. This webinar is an initiative of NFE, National Federation of Engineers for Electrical Safety. NFE's vision and mission is to make every electrical installation free from accidents such as electrocution, fire due to short circuit, and increase the reliability of it. NFE's mission is to achieve our vision through getting accredited for product and personal certification, which shall focus on electrical safety by design, manufacturing, installation, and maintenance of electrical product and installation by competent and qualified manpower using quality resources, including product, processes, and procedures. Please visit the website www.nfes.org to become a member of NFE. The last webinar was about electrical safety in hospitals, enhancing safety in Group 2 medical locations with medical systems. Today's webinar is about power quality measurement, IEC TS 63191 2023. And the speaker for the day is Mr. Haribala, and the moderator is Mr. Sachin Shillar. The speaker, Mr. Sachin Shillar, is an assistant professor and the head of Power Quality Cell at AISSMS, Institute of Information Technology, Pune. With over 23 years of teaching experience and 3 years in industry, he specializes in reactive power management, power quality, and energy conservation. He has published 27 papers, authored 3 books, and has conducted over 250 audits. He established DM Tagar Power Quality Experience Center and held leadership roles in the IEEE Pune section. In 2013, he received a grant from the British and Indian governments to study the UK education system. Professor Scheller is a gold medalist in the bachelor's and master's degrees and is currently pursuing his PhD in power quality. And the speaker for the day is Mr. Haribala, energy management expert. Haribala Subramanian is a passionate energy expert with experience of over 30 plus years in India and the Middle East. He has relentlessly served customers in the region by providing technical consultancy beyond the business development profile. He handled, having worked with many European energy management and power quality measurement companies, he is continuing his support to provide customers in India. He believes only continuous knowledge sharing can provide perennial improvement and increase energy efficiency among customers. Haribala is thorough in his energy management solutions that blend the appropriate device for monitoring, communication possibilities, and software with result-oriented analytics. He is very much interested in energy management, power quality, and residual current monitoring, which encapsulates the full cycle of energy management activities. With this, I would like to call Mr. Professor Sachin Shalar.
Thank you, madam. Thank you for the introduction. Good morning to everyone. I'm today really happy to honor and feel honored to have this session moderated. The topic is power quality, which is very important, and as everyone is aware, in fact, I will, it would not be wrong if I say that anyone who is attending today's session must be experiencing some power quality problem in his or her industry. So power quality has become very important. But as per the theory, if you see, the power quality measurement and monitoring is done either for characterizing system performance, that is benchmarking, or to characterize specific problems, or for predictive just maintenance. But if I go through the industry, and I have seen that people don't do anything only when there is a problem they are doing it. But now power quality is becoming so important due to automation and electronics. I think it is important to have a specific plan, some guidelines, and that's where the standards comes, the IEC standard, and today's topic is going to be on to that, where we are going to get a detailed plan how power quality measurement should be done, what are the things to be characterized, and how records are to be kept. So I'm sure this would be a very interesting webinar, and we have a very interesting speaker who has a lot of experience from, and he has traveled through the various parts of the world. So we can also get that experience, because from Indian point of view, we are very much novice in power quality. We are yet to pick up it. We have just come to digital meters. We have to go to power quality meters, and then power quality measurement, and then monitoring, and then everything will happen. So this, with this short introduction, I would like to invite Hari Bala sir, today's speaker, to deliver the session. Thank you, sir.
Thank you, Sachin. Thank you, Lakshmi, for introduction. I'm just sharing my screen right away. Very good morning to everyone. Hope my audio is clear to all. If I need to reduce my speed of talking, just give me say hi and reduce the speed, then I can probably do that. Invariably, sometimes this happens in webinar, and that's why I'm saying this. Today's topic is IEC TS 63191, demand side power quality management. So we all know power quality. We, in a sense, try to do some kind of power quality management, and we wanted to do it in demand side, but without may or may not be knowing that we are doing it in the demand side. So demand side is basically referring to industries here. I changed this topic slightly different to something called as taming an elephant. So I see power quality as a subject is something like an elephant. So everyone knows half of it, but how do we know to put everything together to form a big elephant? Yeah. So this is the topic. Having said this, in fact, I should also thank NFE for all its efforts for the keep creating a very, very deep understanding and awareness about the safety and security of the electrical system. And in that, power quality is also forming one part of it. I'm very glad for it. So when we have an elephant nicely in a temple or attended by Mahout very nicely, we all like to see the elephant. We all like to go and close to it and see it. It is very nice. But imagine if the Mahout is not giving food to the elephant, and then what it does, it will just go and start having a field day rather than going and spoiling the fields nearby, or maybe the Mahout's own field. It goes and destroys. Power quality is also like an elephant which needs to be tamed. As long as you take care of it, it is very simple, nice, but when it gets out of control, it plays a havoc on the system. So this example, I would start going into the subject, power quality. What is the cost of the power quality in India? So let's just do a small brainstorming. It is estimated around 4% of annual turnover of businesses or industries is lost in power quality. In other words, in Europe and in US, around 120 to 150 billion euro in euro and 129 billion US dollars is estimated to be the loss, and 80% of the PQ issues generated within the industry. These are some of the points which we need to note when we are understanding the whole stuff. This is the research done by EPRI. But in India, how do we estimate power quality? Because unless a problem is reported, then we can estimate. If the problem is not reported, we cannot estimate. So it's very similar to safety. Yeah, you need to have near miss or an incident. So then you start reporting it. Here, many times we do not know that issue is because of power quality problem. So the power quality problem can create different types of losses: production loss, production output, and production output reduces, and then the credibility of deliveries reduces for the company, and there would be continuous failures which are being done. Equipment and component failures, but we just go, electrician goes, changes the fuse, electrician goes, changes the component. So they call it as an operational maintenance or operational maintenance cost, which is normal. But maybe that is due to a power quality problem. And that is why I always say industries in this part of the world do not like to have a heart attack, but they can live with cancer. And power quality is something like a cancer. So this is very, very important subject that industries should take care or should start taking actions or start giving attention to it in much more detail. Why? Because in the previous grids, we had generation, transmission, distribution, and consumption straight in a line, step by step. In IT terms, we call it as a waterfall method. When generation happens, it comes to transmission, and when transmission happens, it goes to distribution, and distribution gives it to the consumers, and consumers happily consume the power. All these things happen at the same time, or in real time, but there is a continuous flow which is centralized and unidirectional. But the current systems nowadays are not that way. It has many generating stations, transmission systems are complex, generating stations are available from a very high voltage to a complete low voltage systems, and it is all inserted everywhere in the network. And then the transmission system is doing a long distance transmission lines crisscrossing all over the country. And then we also have these consumers consuming it at various places, plus they are also injecting into the grid with the help of microgrids and various other things. Plus they also complicate it more by using high efficiency systems, which can potentially create a lot of power quality issues. Yeah. So this is the whole lot of the way in which the grid is there. Someone has raised a hand. Is there anything to raise their hands? Is there anything to say something? Or please put it in chat. Maybe we can do it in the end for the sake of time. Otherwise, we might potentially deviate from the topics as well. So, but I will be able to get these things through. Then, in the complex world of electricity from generation to consumption, there are so many issues. We have fluctuating power in feeds, change in energy flow direction, sources of disturbances measured at PCC, because that is where we are measuring it. And then we come to some kind of conclusion, who is the culprit of throwing a lot of harmonics into the system. Decrease in short circuit capacity of the power system. This is very, very important, because as the system goes dynamic, the short circuit capacity of the power system changes dynamically all through the network. So maybe at the customer's input, or at the utilities input, or at the transmissions side, the short circuit capacities can potentially vary because of the varying kind of energy, different direction of energy flow and stuff like that. So unpredictable fluctuation power field is one of the consequences of renewable power sources. So especially at wind parks and also at the PV installation, the power can fluctuate. Say, for example, in a place where they have connected, say, roughly around 100 megawatt of power, 100 megawatt of power in a particular area through windmills. What happens when the wind stops? The whole 100 megawatt power becomes deficit in no time. And how do you predict the wind? It becomes difficult. So we can only pray. And when at the same levels at the installations of PV installations, it becomes very important where the PV gets connected with the system. So if you connect it in the wrong end, then you have more complications of handling the power factor, or you have complexities handling the various other aspects of the system. Voltage deviations occur very frequently because not all the sources are active always. Sometimes They are switching on and switching off, and the flow of direction also changes in the system. So these are some of the common consequences of the newer grid. And this is what is taken. But what we are doing currently right now is we have standards for transmission system to generating stations on power quality. Transmission systems have power quality standards. Distribution has power quality standards, and consumers also have power quality standards. So most of the time, these are applied at the point of common coupling for various people. So from generator, where it is giving it output to the transmission system, for transmission systems and the utility, it is at the point of common coupling at the grid stations, where the power is getting transferred into the utilities, and then from utilities to consumer, where the power is getting transferred from the utility into the consumers, which we call it as a point of common coupling. And what do we measure at the point of common coupling? Most of the time, we do this and we do the limits. Yeah, limits are the one you say that don't pollute my system beyond this value. This is what they say. Say, for example, in the consumer side, we will say utility will come and say, don't pollute my system beyond 5% of harmonics. Don't throw more harmonics into my system. Your limit is 5%. You can throw, but it is limited to 5%. So there is a limit which is set. So we only try to follow the limits rather than trying to understand what inside is happening inside our system, inside our load sites, for example. So this is much more difficult. So it becomes very difficult for us because we are only focusing on one place. Yes, we have to focus on PCC, but if you have to control that PCC, you need to do much more activities on the load side itself. So that is very important in this part. So what all the standards we have in the relevance for the relevance in the network? You have 61000-2-12-2-2 for transmission, 5160 and IS 17036 for distribution systems, and IEEE 519 for the consumers, where it clearly says voltage is the responsibility of the distribution companies and current harmonics is the responsibility of the consumers. But all these things give limits for harmonics, individual harmonics, TDD, THD, everything is specified, and we have to work within the thresholds what is given in the standards. So in demand side power quality management, which we have right now called as IEC TS 63191. 63191 is basically TS. It's basically a technical standard which will be emerging into a standard soon. Yeah. So we are all lucky to have this information much before so that we can start thinking about it and start working on this. This document provides guidance on how to establish, implement, and maintain demand side power quality monitoring system. So we are going from power quality management to power quality monitoring system. So what is that monitoring system? Monitoring system is basically you measure, understand what it is, and then take a decision. But in this particular standard, it clearly gives us a guidance. How do we measure? What we need to consider for measuring the power quality in the system, in the network or in the consumer's place. So demand side refers to the load side or the industry within an area. Nowadays, it becomes very, very important that industries of a data center, which is a small 5-story building, can consume just like a power, like a big furnace, which is melting iron and steel and stuff like that. So a small area can be more power intensive. So that becomes, which means they are also potential to throw a lot of harmonics by usage or in their loads inside their systems. Yeah. So the scope of the power quality measurement system here is defined here as objectives and constraints, assessment of initial power quality measurement situation, definition of an action plan. So we need to be defining an action plan to improve the power quality measurement system. And then the power quality measuring system is implemented. So wherever there is no devices or measurement system, implementing these devices, installing these devices, in other words, and then taking the data from these devices for the improvement of the power quality situation. Unless otherwise we have the data, it is very difficult to manage the power quality system. So that is why many of the energy auditors try to compensate that by having an instrument themselves, because the customers don't have it or they don't want to have it. So this always happens. That also gives a good business opportunity for the auditors to have an instrument and then do it. But whether that is that be sufficient for the customer to resolve the problems of power quality is a question mark what we have right now today. Yeah. And of course, once you have a good measurement system, we need to maintain it and maintain it as well. In this particular 63191, they have given 6-phase measurement plan. So the measurement plan is for 6 phases. And at the end of 6 phases, we are all going to judge, or we are going to provide scores to the industries that how much their ability to do the power quality monitoring. Once the monitoring becomes perfect, then you also have a set of good application which can come into it. Thereby the solution for power quality mitigation can happen effortlessly. This is the idea, because everywhere there are standards, these kind of problems, these kind of effects, these are the mitigation possibilities. So we know all these things, but we need to measure and see whether you need to take action, and if that action is taken, up to what level, with what kind of mitigation equipment, becomes much more easy. So let me tell you, this standard stops at assessing the ability of the demand side power quality measurement. Yeah, so this is what it is. So that is why it says it gives a levels of DSPQ, that is demand side power quality, as rank 0, 1, 2, 3, which rank 3 is good when you score good marks. In fact, I when I was going through the study of this particular standard, I was feeling very elated, because I'm going to judge someone. We like judging some people, judging some actions, judging how the flight, if you go on flight, I have a habit of, if I go on flight, I have a habit of looking at what is the kind of, I give marks to various activities and try to find out what is the kind of service I have got on that particular date for my own actions, for a simple terms. So, but this has come into standard for the power quality level here. So this is what we are exactly doing over here, ranking it 0 to 1, 1 to 2, 2 to 3. And if we are able to get up to 3, then we are ready for our mitigation aspects itself in a much more higher level. Yeah. You can do mitigation anything, but it's like going and checking for HbA1c and immediate instant sugar level of us, right? Both gives some kind of a parameter. But what happens is, but there is always a possibility of improvement when I do the study from time to time, so that I get to know what is the benefit, what is the amount of investment I need to do, how much I can work out to get things through. So this character is doing this. I always give this example. I have a diabetes. I go to the doctor. They send me to a laboratory. Then they take a immediate sugar level, glucose level. Then they also take HbA1c. And then they say, okay, this is your sugar level. Now I say, I don't accept the sugar level, because my wife is not giving me proper food. That's not my case. I need to do my workout. Then only I can bring down my sugar level. I can't just cannot blame that my family or at home I'm not getting a proper food. That's just not possible, because there is so many things which needs to be considered from our side, from within the industries, so that these scores can be improved. So these scores will give us a guidance, where do we stand, and then where we can improve. So this is the first level of it. So I'm dividing this whole standard into three parts. The first part is the phases of measurement. The second part is the power quality information or the power quality parameters, what we need to monitor. And this standard gives an elaborate information on the power quality problems and the effects, the how to mitigation possibilities, and also the what parameter needs to be measured. So it gives a complete uh, information in the chapter number 5, which is very important for us. So, but it also defines the 6 phases. This is the first part. Second part is the power quality parameters, and third part, what we will be seeing is the how do we evaluate and put points and judge it. Give a judgment on whether how we can improve it. So that's where we are going to. These are the 3 parts. So I would require your attention for the next 30 minutes or so that I will try to compress it and try to give it everything, because this document was almost 120 pages. So I'm trying to put everything together in a gist to make it easy for us to understand and start taking actions on this. So the 6 phases of measurement plan, this is the first part. It says the phase 1 to phase 6. Phase 1 defines the context and objectives. Phase 2 defines the initial situation of PQ measurement in the industry. Phase 3 defines the design and action plan to improve the measurement system. Phase 4 defines implementing the action plan to improve the measurement system. Phase 5, the using of the measurements data. And 6 is to maintain the measurement system. So there are 6 phases identified. We may be doing many of these phases here and there, now and there, in many places as per our requirement. Or if some incident happened, a big tripping happened, then we do this, and then we do some reporting, finish it off, and then go start doing the next work. So this always happens in most of the industries. So let me go into the first phase of value. The first phase, also in every phase, you have the goals, you have the motivations, you have the stakeholders of the organization, including your higher managements, and budgets needs to be allocated for the whole process, all the 6 phases, in fact. And then the planning, how do we do it? How do you plan it? Who will install it? Whether I can install it or I can put someone, contractor, to install it, or we will have the do we have the resources to do the installations and maintenance, collecting data? All those things needs to be done. So the level of measurement is one of the criteria. What it gives here is ability to quantify the power quality by site, by zone, by source, and relevant loads. So we will have to understand or analyze or demarcate our industry as zones by application or by relevant loads to understand, to quantify how much where we need to do power quality monitoring. The second part is the ability to take the readings from the quality points at the regular interval. So we need to be understanding how do we take the readings for better power quality measurement monitoring purposes. And then what are the influencing factors that affects this? So what all the influencing factor affect our power quality within our organization? Maybe it is some kind of a specific loads, or it is some kind of a customer who is a big customer who is adjacent to me is throwing a lot of harmonics. That is also an influencing factor. And then we have to see the monitor, how do we monitor the existing installation power quality, and how do we analyze the power quality situation in our system. These are the major criteria which needs to be defined and factored in the first phase. And then we give the summary of the deliverables. This is more of a planning activity where we say, okay, my last time my DSPQ ranking was this much, and I wanted to go for DSPQ ranking from 1 to 2, and then if I have to go to 1 to 2, what all I can do it. That is the ability on the 5 points which we discussed, put forth will come into the picture, and then we do it. This is phase 1. When it comes to phase 2, we divide the zones. I was telling you, we actually try to create the assess the situation by creating into zones. Say, for example, a zone is a building within the factory area, can be. A zone is a production line, a complete production line. A zone can be, you can create as many as zones in your factory. It is a virtual one, right? So you create, this is the production line for tires, this is the production line for, say, maybe some other rubber products, this is the production line for painting area. So these are all called, these can be created as a zones. And then in these zones, we should have devices. So it also tells what kind of devices you can have. So this standard classifies as two major devices called as PQI, power quality devices, and PMI, power monitoring devices. Yeah. So these are all as per the standards. There are as per the standards, these devices are then 62586 for PQI, and PQI is further defined in a much more better standards. The latest one called as 61000-4-30 as Class A and Class S devices. And then the standards say 61557 for the PMI devices. So now, why should I use two different devices? Because I get one MFM multifunction meter in the market for, say, 6,000 rupees. Why should I install two different types? It becomes easy if I have to maintain my stocks with one devices if something has to replace. That's not the idea. I put that question differently. We don't use the same switchgear, same trip units all through the circuit from incomer to the outgoing. We use it accordingly because there we say protection. Because of protection, because of discrimination, we wanted to have different kinds of system, different kinds of trip units, different kinds of tripping system, different kinds of braking systems, so that we have an idea. We don't use the same MCCB all over from the incomer to outgoing, right? So we always say, no, that is as per the current we do it. So the same way, according to the information what we want, we also have to be using the PQI devices and PMI devices appropriately. Yeah. It also further down, it also classify this PQI devices into two and PMI devices into two, which we will be seeing it as well. And then we need to start seeing how we are able to taking the data reading and storage into the system. This is the phase 2. Yeah. In phase 3, in phase 2 also, the zone, which if I have to elaborate it, probably this is how I elaborate. In a site or a plant or a facility, a zone is a physical area. Under that zone, you have use area or an application area, which can be a simple production line or something else, which we should be able to monitor. So we are dividing a site into zones and uses or applications. So in a painting line number 1 or painting line, certain missions can be classified as uses as well. Or certain painting missions can be, or dryer unit, or the painting unit can be used as an application as uses itself. So I'm just giving an example, but industry is the better people to analyze what kind of zones and what kind of users they have, because we will be judged by the zones and users also. The farther you go drill down, you have a better idea of scoring higher marks. Yeah, that's how it is. So you have zone 1, zones, you have uses and site in the zone classification, which we need to be understanding. So the same way for the power metering and monitoring device and power quality device, PMD and PQI. So this can be a combination of one or more devices of several functional modules. We call it a simple multifunction meter, but no one says what functions it does. We only say it is a multifunction meter. No one have defined clearly what the functional modules are. So this is a very important thing. So we need to know what kind of measurement is that particular meter is doing. The same way for PQI also, what kind of functionality, whether it can be classed as Class A, which is a legally acceptable class function, or a Class S is a statistical evaluation function of measuring power quality parameters. So we need to do this. So what happens here? They have divided this into PMD2, PMD3, PQIS, and PQIA. So this is a very important table where it says what these meters should be measuring at least, so that to be called as PMD2, PMD3, PQIS, and PQIA. So it is a very important table again, which gives us each meter has to be different to be going into the where the users are, the zones are, and the major sites are. Site is predominantly a factory, and their incoming is called as a site, which is defined over here. So these are the 6 phases. In the second phase, we have the zones and users classification. On the devices, we have the PMD devices and PQI devices, and each device, what it can measure, comes in this particular standard. Now the defining the goal of phase 3, actions to undertake, improve, and achieve the organization. So now we understand the second phase. We know what all the points we have. That is in the assessment also, we have certain number of devices, give specific points for us so that we can accordingly mark them for this particular phase. So what is the proposal for improvement action? So probably what we can do is we can target the zones, and this zone I wanted to start with. This zone I wanted to fix certain kind of meters in PQI meters in this zones. These loads, these application loads require more because I have more number of variable frequency drives in this particular application or uses. I will have better meter in these places rather than a PMD products. I will have PQI. So we have to choose accordingly at various zones and in applications, and then try to improve the monitoring system from level A to level B, or level 0 to level 1. So this is very important in doing this. And once we do this, we prioritize the installation of the devices in various places so that we first improve the monitoring perspective of this particular whole system as well. Yeah. So that then we do the review. The fourth action is the installation action. We need to ensure the implementation of this particular process. That is, wherever we want, how do we put the meters, which device we need to put, and all those stuff. We need to start the implementation action, like whether do we have proper CTs, whether the CTs are properly configured and has the relatively reasonable accuracy, which we can use it, or we have to buy a new CT, or we cannot install a CT in that particular place because the panel is having a smaller area. So probably we can use alternative methodologies. We need to be having a look at it in this particular phase. And then the installation and commissioning of the measurement devices starts. So ultimately, by following whoever you are buying these devices from, follow the manufacturer guidelines clearly and the manuals. Generally, many customers do not read manuals. They think that if I know S1 and S2, I can connect the CTs S1 and S2. If I have V1, V2, V3, I will connect the voltages and it is done. But it is always better to understand the manual, which becomes helpful in doing this. So this is one of the criteria in this particular phase, to reading the manuals itself, So we need to be doing that to understand the product perfectly so that we can take as much as benefit out from this product. So that is what is very important. Nowadays, the electronics has improved pretty well, that we can do much more than what we are currently doing in these devices. One of our devices can give an output if there is a voltage low. So a demand control activity. All these things can also be done with these kind of devices. So we need to be understanding these perspective as well in making sure that doing it. MFM means is not only measuring voltage, current, kilowatt, kVA, kVAR, power factor, frequency. It is much more, and that is what we are trying to learn today. Yeah, this is on phase 4. Phase 5 is basically about storage of power quality data, whether you are storing the data in an automatic way or in a manual way, or you have a mix of automatic and manual way from these devices, and then collecting the data into the system. So analysis then comes once you store the data, then you start analyzing the power quality data itself. So it can be done either with an internal expert or an external expert. Having said this, the phase 1 in the stakeholders, we need to be very, very clear that we need to have someone responsible for the power quality within the plant. So a power quality manager is very much required, so that he leads and he becomes accountable for the power quality measurement actions. And then he can do the analysis with a third party or an external experts as well. But it is very important someone leads within the industry the whole power quality as a subject. So this is one of the criteria in phase 1, which we will do. We will also see it in the later part of the slides. Decimation and protection of power quality data. How do we share the data? It becomes very important. This is another industry's vital problem. The maintenance department doesn't want to give certain information to account department, and account department doesn't want some information to be given to maintenance department. And energy manager, who is sitting on top of the maintenance department, who is in charge of managing the energy better, he doesn't have communication with accounts, and he doesn't have communication with the maintenance department. So there is a mix of silos, who are siloed types of people who are working. Then ultimately, no one gets the transparency of the data. So the data needs to be relentlessly shared the same way across the industry stakeholders, so that they get their benefit out of that. Electricity is not only a problem of the maintenance department, it is the problem of the whole company. If it doesn't managed well, then the whole industry is going to suffer. So that is why transparency of data, power quality analysis, and storage is stressed in phase 5 of this. Phase 6 is much more simple. Once you establish the system, then it starts running. You do the firmware updates of the software, because many of the devices nowadays, electronic devices, has the possibility to upgrade by just changing the software inside it. So if a product is able to upgrade the firmware, we do upgrades of Microsoft, we do upgrades of our various other applications. Why not for the meters as well? So firmware updates for these devices should be easily available, and it should be done at site predominantly. So these are some of the phase 6 measurement and maintenance systems, how we do it. So there are 6 phases. We have gone through the 6 phases, and now this is the first part is concluding with this. I will go to the second part and then come back to the third part to relate this with the first part again. So the third part and first part of this particular webinar is more important. So I would like you to stay tuned, because the second topic, what we are going to talk next, is all about power quality disturbances and their impact in the system. So we are going to talk about various power quality disturbances and their impact on the system. One impact is very common to all. Whatever is the power quality, that is the financial loss. Interruption of process creates financial loss. Equipment damage and aging can also causes financial loss. Production loss causes financial loss. Waste of raw material, again a financial loss. Loss of data in a server again could be potentially a financial loss, increased losses in electrical equipment and distribution